In January 1942, Boeing Plant 2 in Seattle was supposed to be tirelessly producing flying fortresses to darken the skies over Germany. Instead, the workshops resembled an industrial bottleneck. 63 B-17 bombers sat unfinished on the assembly line, each an unfulfilled promise from America. The Army Air Forces had ordered 3,615 bombers for delivery within the year. Boeing delivered 9. Just 9. General Henry Hap Arnold, commanding general of the Army Air Forces, wasn't just disappointed, he was furious. At a heated meeting on January 15th with Boeing executives, Arnold stated unequivocally, without bombers, there would be no strategic bombing campaign. Without a strategic bombing campaign, American soldiers would face an entrenched Nazi war machine for years to come. The calculations were simple and terrifying. The problem wasn't a lack of manpower. Boeing had hired over 30,000 workers in 6 months, many of them women who had never set foot in a factory before. Nor was there a problem with materials. Aluminum flowed from Alcoa faster than it could be used. The crisis stemmed from something no one had anticipated. The bombers themselves were too complex to build quickly. Each B-17G required 140,000 individual parts. The wings alone demanded 12,000 rivets per side, joining 7 overlapping layers of aluminum skin to an internal frame designed to withstand forces up to 6 Gs in combat maneuvers. Traditional assembly methods, honed on smaller aircraft, simply collapsed under this complexity. Philip Johnson, Boeing's production manager, walked the floor every morning at 5 a.m. with a clipboard in hand, watching the same nightmare unfold. At Wing Assembly Station Number 4, 17 workers crowded around a single wing section. They got in each other's way. One riveter would finish a seam, step back, and another would need access to the exact spot he'd just vacated. Then a third worker would require that position for another rivet line. The choreography was maddening. Johnson timed it himself, 20 hours and 14 minutes to complete the assembly of one wing from bare frame to final rivet. 20 hours. The British were losing bombers faster over Germany. Every Luftwaffe fighter left unchallenged because American bombers weren't in the sky meant more merchant ships sunk in the Atlantic, more factories operating at full throttle in the Ruhr Valley, more time for Nazi Germany to consolidate its grip on Europe. Boeing's engineers had already tried everything. They redesigned tool access points. They created specialized jigs and fixtures. They even experimented with different crew sizes, thinking fewer workers would reduce congestion. Nothing worked. The core problem remained. The rivet pattern specified in the engineering blueprints required work crews to access the same physical space in an overlapping sequence. The work could not be parallelized. More workers couldn't be added to speed it up. It was a bottleneck embedded in the aircraft's DNA. By late January, Boeing executives were having quiet conversations about the unthinkable, telling the Army they couldn't meet production targets. Some even whispered about bringing in Douglas or Consolidated to take over primary production. On January 28th, a secret memo circulated among senior leadership. The subject read, Assessment of B-17 Program Viability Crisis. No one wanted to be the person who lost the war because they couldn't figure out how to rivet aluminum fast enough. Stay with us and watch until the end. We'd be especially grateful for a like and a subscription. And of course, tell us in the comments where you're watching from. Step into Wing Assembly Station 4 any morning, and you'd see what looked like organized chaos that wasn't actually organized. A wing section lay on a massive jig, a 32-foot skeleton of aluminum ribs and spars. 7 layers of aluminum sheeting, each precisely cut and drilled with thousands of holes, awaited attachment in a specific sequence. The process began at the wing root, where it would eventually attach to the fuselage and moved outward toward the tip. Sounds simple. It wasn't. The engineering blueprint dictated that rivets be installed in rows running parallel to the wing's leading edge. Row 1, then row 2, then row 3, moving back toward the trailing edge. This pattern made perfect structural sense. Each row reinforced the previous one, creating an overlapping shingle effect that distributed stress across the wing's surface. Engineers at Boeing's development center in Seattle calculated every rivet's position to optimize strength-to-weight ratios. On paper, it was beautiful. On the factory floor, it was a disaster. Here's why. To install the first row, a riveter worked from the top surface, while a bucker, the person holding the bucking bar, worked from underneath through the wing's internal structure. They had to be perfectly synchronized. The riveter's pneumatic gun drove the rivet through pre-drilled holes with 3,000 pounds of force. The bucker's bar pressed against the rivet's shank from the opposite side, forming a mushroom-shaped head from the molten aluminum that clinched the sheets together. Miss by half a second, and you had a loose rivet that had to be drilled out and replaced. That added 3 minutes for every mistake. Multiply that by 12,000 rivets, and the errors became catastrophic. But the real nightmare began when the second row started. To access the second row's rivet line, workers needed to position themselves exactly where the first row crew had just been working, except the first row wasn't finished. Not entirely. Quality inspectors had to check every 10th rivet with a bore scope, a tedious process that took 15 minutes per wing section. So the second row crew waited and waited. Meanwhile, the third row crew, already geared up and ready, stood idle, wasting time. The production schedule called for parallel workflows, but the physical reality of the wing's geometry made it impossible. It was simply not possible to position enough workers around the structure to rivet multiple rows simultaneously. Imagine facing a task every day that seems like it could be solved much more simply, but the system won't allow it. Do you feel it, see it, but are powerless to change it? Remember that feeling when you spend precious minutes on absolutely meaningless actions that only slow down the entire process. We've all been there. And today we'll tell the story of how one person, finding himself in such a situation, didn't just accept it, but found a way out that changed the course of history. In this narrative, we'll reveal how a simple shift in perspective can radically transform seemingly immutable manufacturing processes, increasing efficiency exponentially. You probably don't even realize how many hidden reserves lie within the routine operations around you, waiting for someone to notice them. Forget everything you've been told about the inviolability of established rules and blueprints. Sometimes it's the simple worker who sees what escapes the eyes of design engineers. Stay with us and watch until the end, as we'd be especially grateful for a like and a subscription. And of course, don't forget to tell us in the comments where you're watching from. On the vast factory floors where wings for military aircraft were born, a daily drama unfolded. Rivet guns, those clumsy industrial pneumatic hammers, shook the operator's body with each shot, turning the work into an exhausting ordeal. And everywhere, like mad pythons, compressed air hoses snaked around, constantly tangling with electrical cables for inspection lights and creating trip hazards for workers rushing between stations. To move from one position to another, a riveter had to disconnect the air hose, carefully coil it, navigate around 3 colleagues, find a new connection station, reconnect, and only then resume work. This 30-second ritual was repeated up to 70 times for each wing section. Added to this was another, equally insidious problem: heat. January in Seattle may not have been known for warmth, but inside the factory, the atmosphere was entirely different. 17 workers, tightly grouped around a single wing section, each emitting their own heat, and each pneumatic gun adding its share to the confined space, created a greenhouse effect. The aluminum sheets, absorbing this heat, expanded microscopically, insignificantly, just 0.03 inches for every 10 feet of section. But when it came to aligning pre-drilled holes with a tolerance of 0.02 inches, this expansion meant the holes simply wouldn't align. Riveters spent up to 15% of their time using tapered reamers to widen holes that shrunk due to misalignment as the metal cooled. None of these circumstances were accounted for in the engineering specifications, as no one could have anticipated 17 people working in such close proximity for such extended periods. Frank Szymanowski, at first glance, was not at all the kind of man destined to change the course of a war. 31 years old, 5 feet 7 inches tall, with hands permanently stained with aluminum dust and grease, he was typical of his time. Before the attack on Pearl Harbor, Frank worked at the Chrysler plant in Detroit, installing door panels on Windsor sedans. It was monotonous, almost mindless work, where his hands knew what to do before his brain even registered the command. When Boeing began mass hiring in late 1941, Frank moved his wife and 2 daughters to Seattle, rented a room in a boarding house near the factory, and joined the night shift at Wing Assembly Station No. 4. His workday began at 4 p.m. and ended at midnight, 5 days a week, and sometimes 6 when production quotas demanded it. What set Frank apart wasn't his virtuosity as a riveter, as dozens of other workers could match his speed and precision. His unique quality was that Frank couldn't stop observing the entire process as a whole. Most riveters focused on their immediate task: align the gun, pull the trigger, move to the next rivet, repeat 400 times a shift. Frank, however, saw the whole production ballet. He noticed that Jenkins, working on the 3rd row, always waited for Patterson to finish the 2nd row. He saw that Patterson, in turn, constantly waited for quality control to approve the 1st row. He noticed that this sequence created a cascade of delays that grew geometrically as they moved across the wing's surface. On February 4th, during his midnight break, Frank sat on an overturned parts crate, eating a sausage sandwich, and intently scrutinizing a finished wing section being moved for final assembly. Something about it bothered him. The rivet pattern looked impeccable from a structural standpoint. Each row overlapped the previous one, creating that shingle effect engineers loved. But Frank kept recalling his previous work at Chrysler. When installing door panels, they didn't start from one edge and move across the entire surface. They started from all 4 corners simultaneously and worked toward the center. Why? Because it allowed 4 workers to labor in parallel without getting in each other's way. The geometry of the door panel made such parallel work possible. He looked again at the wing diagram posted on the station's bulletin board. The rivet pattern showed straight lines running from the leading to the trailing edge, parallel rows marching across the wing's surface. But the wing itself wasn't a flat rectangle. It was a complex three-dimensional structure with depth, with internal ribs creating separate compartments, with access points in specific locations. What if the rivet sequence followed the actual geometry of the wing, rather than treating it as a flat sheet? What if work began from multiple points simultaneously? Points chosen because they provided workers with maximum physical access without overlap. Frank grabbed a pencil and began sketching on the back of his time card. Instead of straight rows, he drew a pattern that seemed almost random. Rivets clustered around structural ribs where access was easiest, then diverging lines connected these clusters, following the natural contours of the wing's internal structure. It looked wrong. It seemed like someone had just scattered rivets across a blueprint and decided to leave them where they fell. But as Frank traced the pattern with his finger, he realized something critically important. 5 workers could simultaneously install rivets, and not one of them would require the same physical space. The first worker could be at the wing root inside the main spar. The second worker could work in the mid-wing section, accessing it through an inspection panel. The third worker could handle the trailing edge, which was shallow enough to rivet from top to bottom without a bucker. They would never intersect. The structural implications of his idea worried Frank. The engineering blueprint prescribed that parallel row pattern for a reason: load distribution, stress concentration. Terms Frank only half understood. But he kept thinking about something else he'd noticed. Rivet failures almost never occurred where 2 rows met. They happened at transition points, where wing skin thickness changed, or where cutouts for fuel tanks interrupted the pattern. The rows themselves weren't magical. They were just one way to distribute fasteners across a surface. Perhaps not the only way. Frank knew perfectly well what would happen if he approached a production supervisor with his sketch. He would be politely smiled at, informed that engineers had spent months calculating those rivet positions, and sent back to his station. The hierarchy at Boeing Plant No. 2 was rigid. Engineers designed, supervisors managed, workers assembled. No one expected innovation from a man whose job title was Riveter Second Class. Have you ever thought that such a seemingly simple action as riveting could become a stumbling block for an entire aircraft manufacturing company? What if conventional work methods, considered the gold standard, are actually slowing progress and jeopardizing the future? Imagine being on the verge of unemployment, and only a radical, seemingly absurd idea can save not only your career, but thousands of jobs, as well as the fate of an entire industry. Does that sound familiar? Perhaps you too have encountered situations where a system designed to help actually hindered, and the solution was found where no one expected it. Today we'll delve into a story that will show how one man's courage and another's unconventional thinking changed the approach to aircraft manufacturing, and with it, the entire aviation industry. Frank was on the second rung of the riveter hierarchy. He did, however, have one significant advantage. He worked the night shift, and the foreman of that shift, Bill Hendricks, was different from the others. Hendricks himself had started as a sheet metal worker before being promoted to foreman in 1940. He genuinely listened to the shop floor workers, which, depending on your perspective, made him either remarkably progressive or dangerously naive. On February 11th, during the 8 p.m. shift, Frank intercepted Hendricks and showed him his sketch. Hendricks studied it long and hard. Then he said something Frank hadn't expected. "This violates every principle of structural load Boeing uses. You know that, don't you?" Frank nodded. He knew, or at least suspected. Hendricks continued his thought. "The parallel row arrangement isn't accidental. When the wing flexes under load, stress concentrates along predictable lines. The rivet rows are placed perpendicular to these stress lines. This is fundamental knowledge. It's in every aerospace engineering textbook, published since 1927. The principle Hendricks described was developed by Theodore von Karman and his team at Caltech in the late 1920s. They mathematically proved that fastener patterns in load-bearing structures must follow stress trajectories, invisible lines of force that pass through metal under pressure. The B-17 wing, carrying 6,500 pounds of fuel, plus the structural weight of 4 engines, experienced colossal bending stress during flight. The bottom surface was under tension, trying to stretch. The top surface was under compression, trying to contract. Right in the middle, along the neutral axis, the stress approached zero. Von Karman's equations showed that fasteners should be densest, where stress was highest, and could be sparser, where stress was minimal. The parallel row pattern perfectly achieved this goal. Each row corresponded to a specific amount of stress, and the spacing of rivets was calculated according to load requirements. Stay with us and watch until the end to find out how this captivating story concludes. We'd be especially grateful for a like and a subscription. And of course, tell us in the comments where you're watching from. Frank's scheme completely ignored all these principles. His clusters placed dense groupings of rivets around structural ribs, not along stress lines. His radial connections followed ease of access, not load paths. From a classical engineering perspective, it was nonsense. The wing might survive taxiing tests, perhaps even the first few flights. But under sustained combat loads, microcracks would inevitably form where the rivet pattern didn't match the stress pattern. These cracks would propagate, and the wing would fail. People would die. Hendricks explained all this to Frank right on the noisy factory floor, shouting over the pneumatic rivet guns. Then he asked the question that changed everything. But did von Karman factor in assembly efficiency as a structural component? Frank looked confused. Hendricks continued, "If it takes us 20 hours to rivet a wing, and we're making mistakes because workers are exhausted, cramped, and tripping over each other, how many of those 12,000 rivets are actually installed to spec? How many are slightly loose because the riveter missed the timing? How many holes are slightly reamed because they didn't perfectly align? Your scheme might be theoretically weaker. But what if it produces practically stronger wings because the quality of installation is perfect?" It was pure heresy. Boeing's quality control processes assumed that workers followed procedures precisely. Procedures were developed based on engineering specifications. If wings failed quality inspection, workers were retrained or fired, and more skilled ones were hired. Redesigning the aircraft to accommodate worker limitations was unthinkable. It was backward thinking, the tail wagging the dog. But Hendricks had seen a few things in his 3 years as a supervisor. He saw that theoretical perfection and practical reality diverged far more than engineers wanted to admit. He saw riveters so exhausted by the 18th hour of wing assembly that their hands trembled. He saw riveters missing their mark because they had been in the same position for 40 minutes, their legs cramping. He saw quality inspectors approving slightly loose rivets because rejecting them would mean another 2-hour delay, and production quotas were already unattainable. What if Frank's incredible pattern, by reducing assembly time and worker fatigue, actually led to more reliable and perfect installations? Stay with us and watch until the end to find out how this exciting story concludes. We'd be especially grateful for a like and a subscription. And of course, let us know in the comments where you're watching from. Hendricks folded Frank's sketch and put it in his pocket. "I'll talk to someone," he said. Frank returned to his rivet gun, expecting nothing. Hendricks didn't go to the chief engineer. That would have been suicide. Oliver Eccles, Boeing's head of engineering for the B-17 program, had a reputation for eating alive shop floor supervisors who dared to challenge his designs. Instead, Hendricks went to Donald Douglas, no relation to the aircraft company, who was an assistant production manager and had only 3 weeks left before being fired if production numbers didn't improve. Douglas was desperate enough to listen to insane ideas. On February 18th, Douglas looked at Frank's sketch for about 30 seconds before saying, "This is garbage. Get it out of my office." Hendricks didn't move. He pulled out his notebook and showed Douglas something else. The wing assembly time logs from Wing Station 4 for the past 6 weeks. Each wing took between 19 and 22 hours to assemble. Not a single deviation, not a single crew had found a way to work faster. The bottleneck was structural, inherent in the process itself. Douglas looked at the numbers, then back at the sketch. Even if it works for efficiency, Eccles will never approve it. Never. He'd rather shut down the factory than rivet a wing with a non-standard pattern. This is what Douglas understood, and Hendricks didn't. Boeing was weeks away from completely losing the B-17 contract. Consolidated Aircraft was actively lobbying the U.S. Army Air Forces, arguing that their B-24 Liberator was easier to manufacture and could be produced in greater numbers. General Arnold was listening. If Boeing didn't demonstrate dramatic production improvements by March 15th, the Army would divert orders to Consolidated and other manufacturers. Boeing would retain some production but lose its position as America's primary heavy bomber supplier. This meant layoffs, the collapse of Seattle's economy, and Douglas losing his own job. Douglas, making a decision that violated about 17 different Boeing protocols, authorized a test without engineering approval. He couldn't do it during the day shift, when senior management was on the floor, nor could he do it during the evening shift, as too many people might notice. So he scheduled the test for the night shift, February 21st, starting at midnight. For this, he took a wing section already rejected for other quality control reasons, a damaged spar that rendered it unusable for flight. That way, in case of catastrophic failure, they wouldn't waste a good wing. He assigned Frank and 4 other riveters, veterans of the evening shift who volunteered, and he told absolutely no one else. The test began at 0014. Frank had spent 3 days refining his pattern, precisely determining which groups of rivets went where, calculating sequences that allowed all 5 workers to operate simultaneously. He color-coded the drawing. Red for worker number 1, blue for worker number 2, green for worker number 3, yellow for worker number 4, purple for worker number 5. Each color designated a physical zone that did not overlap with any other color zone. Workers could literally rivet simultaneously without coordinating, without waiting, without bumping into each other. It looked insane. Traditional riveting had a rhythm, a sequential logic. This was like controlled chaos. One worker was inside the main spar cavity. Another was under the trailing edge. A third worked from above, near the leading edge. They didn't follow rows. They followed clusters. And these clusters seemed chaotically scattered. Douglas stood 30 feet away, stopwatch in hand, chain smoking. Hendricks stood beside him, silent. Every 15 minutes, Douglas checked his watch and recorded the time. After 2 hours, the wing should have been about 20% complete. It was 45% complete. The workers began to realize something unusual was happening. They weren't waiting, not for each other, not for inspectors, not for access. Every rivet position Frank marked was indeed accessible without interference. Pneumatic hoses didn't tangle because workers didn't cross paths. Heat was lower because they weren't crowded into one area. The aluminum didn't expand as much because 5 heat sources distributed across the wing's surface created a less concentrated heat load than 17 sources in one spot. At 02:21, 127 minutes after starting, the last rivet was installed. Douglas pressed the stopwatch. He said nothing. He walked to the wing and began spot-checking rivets, pulling out his borescope to verify proper head formation. Hendricks held his breath. Frank stood, covered in aluminum dust, trying to read Douglas's expression. Douglas inspected 30 rivets before he could believe his eyes. Each one was perfect. The heads were uniform, properly seated, with no gaps between the aluminum sheets. He called Jimmy Chen, the night shift quality inspector, without explaining what he was inspecting. Chen took his tool kit and began a full inspection protocol, the same one he had performed on 200 previous wings. He checked rivet spacing with calipers. He used a thickness gauge to check sheet metal compression. He tapped each rivet head with a small hammer, listening for the dull thud that indicated proper seating, as opposed to the hollow ring of a loose rivet. 40 minutes later, Chen looked up and said, "It passes. I don't know which crew did this, but the work is clean." Douglas told him how long it took. Chen thought he was joking. Then he thought the stopwatch was broken. Then he double-checked his inspection, because wings riveted that quickly shouldn't be so clean. There should have been errors, haste, something wrong. He found nothing. The wing was perfect. Better than perfect, in fact. Chen had been inspecting B-17 wings since July 1941 and kept a personal defect log he never showed management. On average, a wing had 140 rivets requiring attention during quality control: loose rivets, misaligned holes, installation errors. This wing had 11, less than 1/10 of the usual defect rate. But passing visual inspection didn't mean the wing would withstand flight loads. The rivet pattern was still completely wrong from a structural engineering perspective. Douglas knew they needed real tests, ones that required equipment and authorization he didn't have. At 03:30, he made another unauthorized decision. He called the night crew at Boeing's test stand in Building 7 and told them to prepare for an emergency load test. He didn't mention that the wing used an unapproved rivet pattern. He simply said they needed an urgent test of a wing section for production verification purposes. The test stand had equipment designed to simulate flight loads. A massive hydraulic press could apply up to 150,000 pounds of force to a wing section, bending it up and down to replicate the stress of flight maneuvers. Standard B-17 qualification required wings to withstand loads equivalent to 2 times the aircraft's maximum weight without permanent deformation. This was the safety margin. U.S. Army Air Force's specification R-1816B, established in March 1941, mandated these tests for any structural modification to production aircraft. Douglas was about to test a wing that violated R-1816B in every conceivable way, using a facility not authorized for non-standard tests. At 04 AO, with no one watching, they mounted the wing section in the test frame. At 04:15, the hydraulic press engaged, applying upward pressure that bent the wing tip upward. Douglas watched the strain gauges. At an equivalent load of 1G, the wing flexed normally. At 3G, still normal. At 6G, the deflection precisely matched the specification. At 6.2G, the qualification threshold, the wing held. No creaks, no popping rivets, no cracks forming in the aluminum skin. Douglas told the operator to continue. At 7G, the wing was still structurally sound. At 8G, individual rivets near the wing root began to show deformation, but this was expected. The wing root bore the highest loads and was designed to be the first point of failure. At 8.4G, the test was stopped not because the wing broke, but because Douglas was afraid of breaking the test equipment. Have you ever felt that your efforts, despite their scale and meticulousness, seem to dissolve into thin air, failing to yield the expected results? Is that feeling familiar when you pour your heart, time, and energy into something, yet the world around you continues on its old tracks, ignoring your innovations? Surely each of us has faced a situation where a seemingly perfect solution crashed against a wall of tradition and established rules. Yet, it's precisely beyond that wall where true breakthroughs hide, capable of overturning conventional thinking. In this video, we'll uncover the secret of how one bold decision, made against all norms and protocols, not only changed the course of history, but also revealed that true efficiency sometimes hides where it's least expected. We'll tell the story of a person who dared to challenge the system to prove that, even within the strictest frameworks, a path to incredible achievements can be found. And believe us, his story will make you rethink your own impossible tasks. Stay with us and watch until the end, as we'd be especially grateful for a like and a subscription. And of course, tell us in the comments where you're watching this video from. We'd love to know where our viewers are sharing these fascinating stories with us. You're making this mistake in every project, but don't notice it, losing precious time and resources. Today, we'll show you how to avoid this trap by following the example of an engineer who dared to go against the current. How often do we overlook the obvious, following outdated instructions like programmed robots? In this video, we'll reveal the secret to exceeding expectations and achieving outstanding results by breaking conventional patterns. Forget everything you've been taught about standard procedures. It's a lie if it prevents you from seeing true opportunities. Stay with us and watch until the end, as we'd be especially grateful for a like and a subscription. And of course, tell us in the comments where you're watching this video from. We'd love to know where our viewers are sharing these fascinating stories with us. So we've already touched upon the importance of capturing the viewer's attention from the first seconds, but the true magic of video content lies in its ability to sustain that interest throughout the entire narrative. This is where the concept of the infinite hook comes into play, allowing you to smoothly transition from one idea to the next, creating a single, continuous story. Its essence is that each semantic block of your video contains a subtle but intriguing hint at the next, making the viewer eagerly anticipate what's coming. Imagine your video as a fascinating journey, where each turn in the road only intensifies the desire to know what lies ahead. The viewer shouldn't experience abrupt transitions or starts of new sections. For them, it's a cohesive, unified narrative where one idea naturally gives way to another, fueled by a new hook. All these internal divisions into blocks exist only for you, as the creator, to help structure the material. For the viewer, there's only one thing: an engaging video that holds their attention every second. By using this approach, we create not just a collection of separate facts or tips, but immerse the audience in a continuous flow of information, where each element logically stems from the previous one, and the next already entices with its mystery. This allows for maintaining a high level of engagement and ensures that the viewer watches the video to the end, as each new segment will seem to them an integral part of the overall captivating story. This is precisely the power of the infinite hook, creating an unbroken chain of interest that holds the audience's attention from the first minute to the last. Have you ever felt like you're hitting an invisible wall, trying to solve a problem that seems to have a simple solution? Do you think your efforts are futile, and traditional methods only worsen the situation? Perhaps you're missing something fundamental. Each of us has experienced moments when, by following all the rules and instructions, we only achieved mediocre results. I've been there myself, on the verge of despair, when it felt like the system was working against you. But what if the true breakthrough lies not in stubbornly following protocols, but in the courage to rethink the very concept of right? Today we'll dive into an amazing story that forever changed the face of industry and proved genuine innovations are born where someone dares to look at things differently. In this video, we'll reveal how one seemingly minor change, made against all engineering canons, not only accelerated production manifold, but also influenced the outcome of one of humanity's greatest wars. You are making this critical mistake in every one of your projects, without even realizing that it's what separates you from tremendous success. Forget everything you've been taught about correct structure and ideal efficiency. It turns out that what seems like chaos can be the embodiment of a higher order. Stay with us and watch until the end, as this journey will change your perception of possibilities. We'd be especially grateful for a like and a subscription. And of course, tell us in the comments where you're watching us from. We're very interested to know our geography. When the hydraulic pressure was released, something inexplicable happened. The wing spontaneously returned to its original neutral position, showing not the slightest residual deformation. Absolutely none. By all laws of aerodynamics and material science, after an 8.4G load, even a microscopic residual bend should have been noticeable. But this wing behaved as if it had only undergone a 5G overload. Engineer Chen, astonished, restarted the inspection protocol, carefully checking every rivet under maximum stress. Not one had loosened. Not one showed signs of microscopic slippage. This wing, against all odds, proved to be phenomenally stronger than standard designs. Standing there at 5:47 a.m., Douglas struggled to comprehend what he had witnessed. Frank's rivet pattern concentrated around the wing's main structural ribs, the very elements that bore the lion's share of the load. Completely unintentionally, by focusing the fasteners in the strongest parts of the structure, Frank had created a pattern that didn't resist the wing's natural load distribution paths, but rather reinforced them. The radial connections between rivet clusters acted as secondary stress distributors, diverting loads from potentially weak points. This wasn't a random arrangement, it was an organic solution, perfectly aligning with the actual flow of forces through the structure, rather than how engineers believed they should flow. By 6 o'clock on February 21st, Douglas realized he needed to present this discovery to someone with real authority for full-scale implementation, not Eccles, who, by his principles, would immediately reject any initiative. Without delay, he headed to James Murray, Boeing's vice president of operations, waking him at his Laurelhurst home. Murray arrived at the factory by 7:15 a.m., still in his casual clothes, and demanded to see absolutely everything: test data, inspection reports, time logs. He watched carefully as Douglas's hands trembled while he explained that they had undertaken these actions without proper authorization. Murray's face remained utterly impassive, betraying no emotion. Don't switch away, as the most interesting part is yet to come. Support us with a like and a subscription if this story inspires you. And don't forget to mention in the comments which corner of the world you're watching our channel from. And then Murray asked the only truly important question: can we train 200 riveters to use this pattern by Monday? Douglas, consumed with proving the concept's viability, hadn't thought at all about scaling. But Murray was already doing the math in his head. If a single wing's assembly time was cut from 20 hours to 2, and Boeing had 42 wing assembly stations, that meant a 10-fold increase in wing production without additional personnel. Wings were precisely the bottleneck of the production line. Fuselages were assembled faster than they could be mated with wings. Tail sections piled up in warehouses, awaiting aircraft readiness. The entire production chain was constrained by the speed of wing assembly. Removing this obstacle would set everything else in motion. That morning, Murray made a decision, disregarding Eccles's furious objections, the protests of the entire engineering department, and Boeing's legal department's ominous warnings about potential liability if wings failed in combat. Murray ordered the new riveting pattern implemented across all production lines effective February 25, 1942. He gave Frank Smansky a $40 per week raise and the title Production Methods Specialist. Hendricks was promoted to Senior Supervisor. Douglas was told his job was safe, and Murray told Eccles that if he didn't like it, he could personally explain to General Arnold why Boeing was still only producing 14 bombers a month. The results were astounding, literally changing the perception of what was possible. In March 1942, the Boeing plant in Seattle produced 47 B-17 bombers. In April, that number doubled to 91. By June, they were already manufacturing 186 aircraft. But the real explosion occurred in July when all 42 wing assembly stations were completely re-equipped with Frank's scheme, and workers had perfected the new sequence of operations. July's output was 284 B-17s. In August, it was 319. In September, a staggering 362 bombers rolled off the assembly line in a single month. This surpassed the entire annual production volume for 1941. The impact on the air war was immediate and devastating for the Luftwaffe. In October 1942, the 8th Air Force conducted its first raid involving over 100 bombers, targeting industrial facilities in Lille, France. The Luftwaffe was initially designed to fight defensively against groups of 20 or 30 bombers. They could encircle these formations, pick off stragglers, making each mission costly enough to be unsustainable. But 100 bombers. The defensive fire from so many B-17s created overlapping fields of fire, making fighter attacks tantamount to suicide. German pilots nicknamed it the Wall of Lead. They were losing 3 fighters to shoot down 1 bomber, and the Americans kept coming. By January 1943, the 8th Air Force was already flying missions with 300 bombers. By summer, that number grew to 500. Each of these aircraft required only 2 hours for riveting instead of 20. Each carried 4,000 pounds of bombs, penetrating deeper into Germany than Hitler could have imagined. The famous Schweinfurt-Regensburg operations in August 1943, raids that dealt a critical blow to German ball-bearing production, required 376 B-17s. Without Frank's scheme, Boeing simply wouldn't have been able to build so many bombers by August 1943. The entire strategic bombing campaign, whose efforts diverted German fighters from the Eastern Front and forced the Luftwaffe into an unbearable war of attrition, depended entirely on Boeing's ability to literally flood the skies with flying fortresses. The Boeing Seattle plant was not the only facility using Frank's scheme. By April 1943, Boeing Wichita, Douglas Long Beach, and Lockheed Vega had already implemented modifications of it. The total production of heavy bombers across all these facilities reached 512 units in a single month. The Germans, of course, were producing 1,000 fighters monthly to counter them. But this was no longer decisive. It's impossible to win an air war when the enemy builds bombers faster than you can shoot them down. Frank Szymanski never became famous. In July 1943, he received a commendation from the War Production Board, a certificate signed by a man he didn't know, which hung in his daughter's bedroom until she moved in 1959. Boeing gave him that raise and a fancy title. However, after the war ended during the 1946 downsizing, the position of production methods specialist was quietly eliminated. Frank returned to Detroit, worked at the Ford plant for 23 years, and died in 1971, never knowing that his riveting scheme had fundamentally changed aircraft manufacturing methods. Because it truly changed everything, not instantly or obviously, but the principle Frank stumbled upon became a new doctrine. In 1947, when Boeing began designing the B-47 Stratojet, its first swept-wing jet bomber, engineers no longer started with theoretical riveting diagrams. They first consulted with assembly line workers regarding access points and workflow organization. The B-47 wing used a pattern that might have appeared chaotic on paper, but allowed 6 workers to complete the riveting in just 3 hours. No one called it the Szymanski method. No one even knew Szymanski existed. They simply learned that matching riveting patterns to assembly realities rather than pure structural theory allowed for better and faster aircraft production. Have you ever encountered a situation where a seemingly brilliant, meticulously planned idea turned into a real nightmare in practice, when something that was supposed to simplify only complicated every step, consuming invaluable time and effort? Perhaps you too felt that your intuitive understanding, born from real experience, was being ignored in favor of abstract theories. In this video, we'll dive into an astonishing story that revolutionized how the most complex machines on the planet are built. We'll uncover how a seemingly simple idea born not within university labs but directly on the production line, not only significantly accelerated aircraft construction, but also forever changed the philosophy of design in the aerospace industry. Get ready to learn why sometimes the most effective solutions come not from the most educated, but from the most observant. Stay with us until the end, as every minute of this story unveils the true secrets of efficiency. We'd be especially grateful for your like and subscription. And of course, don't forget to comment where in the world you're watching us from. This revolutionary concept, in essence, spread rapidly. Douglas Aircraft successfully applied the very same principle to its famous DC-8 aircraft in the late 1950s. Lockheed, in turn, used it to create the legendary C-130 Hercules military transport plane. When Boeing engineers were developing their first commercial jetliner, the 707, they took an unprecedented step, including assembly line supervisors in the initial design reviews. This was truly a groundbreaking decision, to ask those who would actually build the aircraft how manufacturable its design was. The 707's fuselage panels utilized a method that Boeing internally called cluster riveting, which was essentially Frank's pattern, but now under an official corporate name. This approach allowed for a 60% reduction in the 707's fuselage assembly time compared to its predecessor, the Stratocruiser. The true legacy of this story manifested in the modern philosophy of aerospace manufacturing. There's a fundamental principle known as design for manufacturability, or DFM, which every aerospace engineer learns in college. This principle now states that the elegance of a design is measured not only by its performance characteristics, but also by how efficiently it can be produced. A classic example taught at MIT, Caltech, and every aerospace engineering program worldwide is the riveting of the B-17 wings. Students are shown how a theoretically optimal pattern proved less effective than a practically optimal one. How reducing assembly time not only didn't degrade quality, but actually improved it. However, most students will never learn about Frank. They study Boeing's innovative program for developing manufacturing methodologies, as if it were a collegial committee decision, not the insight of one person. Please stay with us and watch until the end, as every minute of this story unveils the true secrets of efficiency. We'd be especially grateful for your like and subscription, and of course, don't forget to comment where in the world you're watching us from. Modern aircraft, such as the Boeing 787, push this idea even further. The 787's fuselage sections are joined using computer systems that generate fastener patterns that appear random at first glance, but are actually optimized for robotic installation. Each such pattern is created by complex algorithms that simultaneously account for structural loads, assembly access, thermal expansion, and 24 other variables. Amazingly, Frank was doing the same thing in 1942, using only a pencil and a stopwatch. He simply lacked the mathematical framework to prove why his method worked. But he possessed something far more valuable, a unique ability for pattern recognition, developed from observing thousands of rivets installed, and the knack for noticing exactly what slowed everyone down. And therein lies the uncomfortable truth this story reveals. Frank wasn't smarter than Boeing's engineers. He didn't have a better education. He didn't understand von Karman's stress equations or load path analysis. He had a different kind of knowledge. He knew how tired you get when you're in the same position for 40 minutes straight. He knew how pneumatic hoses get tangled when workers cross paths. He knew that theoretical perfection, executed poorly, yields worse results than theoretical imperfection, executed flawlessly. Boeing's engineers knew how to calculate stress. Frank knew how to actually build things. Both types of knowledge were vital. Yet, only one was valued. The aerospace industry eventually realized this, but it took decades. Modern aircraft development uses integrated product teams, where machinists and assemblers work side by side with engineers from day one. When Airbus designed the A380, the largest passenger aircraft ever built, assembly line workers had veto power over design decisions that could make manufacturing impossible. This is Frank's true legacy, not a specific riveting pattern, which is now obsolete in the era of automated fastening systems. The legacy lies in the idea that the person doing the work can understand that work better than the person who designed it. What was revolutionary in 1942 is now common sense, except we constantly forget it and are forced to relearn. Every innovation cycle produces its own Frank Szymanski, someone who sees the obvious solution that experts are too educated to notice. Smart organizations listen. The rest continue riveting wings for 20 hours and wonder why they're losing.